Okay, let's start. We are honored to have Professor Chongying Dong from University of California at Santa Cruz to give us a talk today. Professor Dong is a leading expert in vertex operator algebras and related topics. And his topic today is orbifold theory and modular extensions. Let's welcome Professor Dong.
Okay. First, I would like to thank Professor. Okay. Professor Wang for the invitation. Okay. So, Professor Wang asked me to speak in English. Okay, no problem. So, I think this I talk about this. I think several times already, but I'm not sure people in this audience, have heard my talk. But in any case, it's difficult for me to make a new PPT. It's always a problem. So I just use this talk about this topics again. Okay, my talk will consist of 3 parts. Okay, just the first part, introduction. Second part about fusion category. I'm fusion. I see this typo. Okay, okay. So I think most people here probably are very familiar with the fusion categories. If people are very familiar, I just skip a lot of things. Okay, just let me know. Okay, the last part is about our recent work on orbifold theory and the minimal modular extensions. So first, I just started from this vertex operator algebra, and I think this is basically idea of Mossberg. Mossberg, I think this one, I'm pretty sure, according to their paper, this idea comes from Wheaton. They basically in their paper they make a following claim: said every rational conformal field theory should come from basically affine VOA, affine conformal WZW models, and also minimal models associated to this so-called versorial algebras, and also include lattice VOAs. I call it lattice, this called torus, I think conformal field theory, and through 3 constructions to obtain, you can basically get every rational conformal field theory from 3 basic class conformal field theory, rational conformal field theory, by these 3 constructions. One is so-called extension. You have so-called like simple current extension. Second one is called orbifold theory. The last one is called coset construction. Okay, this was the idea in Mossberg's paper. From point of view, so this one always, I think mathematicians are not very happy with this terminology, because they always ask, when you talk about orbifold theory, it's like a geometry. You should have manifold. You should have manifold with the action finite group. But here we just use terminology from physics. So-called orbifold theory in vertex operator algebra is the following. Suppose with vertex operator algebra, G is a finite automorphism group of V. So-called orbifold theory study the fixed point vertex operator algebra VG and its module category. So it's just we call this orbifold theory. Here we don't have any geometry, no manifold, just pure algebraic, I think, terminology. The main feature of studying orbifold theory is you have so-called twisted modules. Twisted module, this twisted module is not a module, but when it restricts this twisted module to a VG module, it just becomes an ordinary module. So in other words, if you want to understand the module for fixed point vertex operator algebra, we have studied so-called G-twisted module. There are no classical analog of twisted modules. Okay, in classical representation theory, there are no concepts so-called twisted modules. I think the difficulty, I think, for studying orbifold theory is we know it exists, we know how many, but we don't know how to construct it. This is always a challenge. So it doesn't matter from point of view geometry, alignment or topology, and also I think, but in conformalness, they always realize representation in terms of automorphism. But it's very difficult to see how to write down this twist sector. It's still, I think, a challenge. And a vertex operator algebra is called, again, we borrow this concept from physics In physics, we talk about so-called two-dimensional rational conformal field theory. So this is how we use this same definition for vertex orbital algebra. So it's if the module category is semi-simple, this is analog of finite dimensional semi-simple associative algebras and semi-simple Lie algebras. For semi-simple associative algebra, we know there is so-called internal definition. Jacobian radical equal to 0, algebra, this solvable radical equal to 0, and so on. But for vertex orbital algebra, we just use this one. So from if you use the analog, really should call it semi-simple vertex orbital algebra. But we know use this terminology from physics, just means modular category semi-simple. Of course, this one is just analog of finite dimensional semi-simple associative algebra or finite dimensional Lie algebra. What's good thing about the rational? Okay, if V is rational, then you can prove there are only finitely many equivalent irreducible modules. From this point of view, this view just look like closer to associative algebras, because Lie algebra, even SL2, there are infinitely many finite dimensional irreducible modules. Then we just measure twisted modules. If V is rational, then you can prove V is G rational or G twisted sectors. Okay, so any G twisted module, GV or any G twisted V module is completely reducible, or the twisted module category is semi-simple. So rationality implies vertex orbital algebra G rational for any finite order automorphism. Here is the Orbifold theory conjecture. Okay, if V is rational, then VG is rational. So this is why this one more Selberger's idea. If you can use the Orbifold theory to get a new rational conformal field theory from a rational conformal field theory. So Orbifold theory. So this one, but this one in mathematics is still I think a conjecture, largely conjecture. But in conformalness, this is theorem. Okay, in conformalness, this is theorem. If you have this, but this is not a theorem in vertex orbital algebra. Second one is any irreducible VG module appears in a irreducible G twisted module. So this is why we need to start twisted module. If you want to classify VG modules, we have to study twisted modules. Kala and Miyamoto in 216 prove if G is solvable, then and V is additionally we assume V is rational and C2 cofinite, then the fixed point VG is rational. McRae in 219 prove conjecture 1 is true if you assume V is rational. Of course, then VG is C2 cofinite. But of course, VG is C2 cofinite. It also implies V is V is C2 cofinite. Okay. Then in a joint work with Li Ren and Feng Xun, we prove part 2 follows from part 1. Okay, so conjecture is solved for solvable group G. Our objective is to understand VG module category, okay, in terms of so-called minimum modular extensions. Okay, this is our goal. Okay. By the way, I want to mention rational vertex orbital algebra V is called holomorphic if V is the only irreducible module for itself. Holomorphic VOE. Okay. This is we will spend a lot of time talk about holomorphic VOEs. Now I just fix notation. Okay. Suppose G is a finite group. HG is all holomorphic VOEs such that G is an automorphism group of V. Okay, so we have G, so we have HG is all the holomorphic VOEs with G action. Then I use the CVG, means VG, this CVG means the VG module category. This is VG module category. With holomorphic, I use the CVG, the VG module category. Okay. And then I just use this equivalence. This is called braided equivalence. Okay. Then yes, RG is all rational VOEs such that G is automorphism of V. And S is also equivalence class of all this CVG with rational VOEs with G action. Okay, again, up to equivalence, up to braided equivalence. So I introduce these two. We have HG holomorphic VOEs with G action, RG rational VOEs with G action. A is just the module categories up to equivalence. Okay, and S is similar for the rational VOEs with G action. So here I just mention the main result in my talk. Suppose a fixed point is rational C2 coefficient, then for every V holomorphic, CVG is the braided equivalent to the module category of Twitter Drinfeld double d alpha G for some 3 cocycle alpha with coefficients in S1. Here S1 means U1, unit circle. Okay. Second is I just mentioned this A. This A is the this is all the equivalence class of module category CVG. Okay. This one is a finite abelian group isomorphic to a subgroup of this third cohomology group. This is how we define the product. You have two module categories. The product given by, because if with the VOE, use VOE, the tensor product is still VOE. G has diagonal action. So therefore, you can still G can be realized as automorphism group of V tensor G. Then you consider fixed point again. This one is just a new category. So it's just how we define the product. And also, this group XS freely. The action again is here is V is holomorphic, W is a rational VOE with G action. So this is just how we define action. Okay, so this action is free. Okay, I also want to mention if alpha is pointed. Okay, I'm going to explain each concept I think later on. Then there exists a positive definite even modular unimodular lattice error such that G is the automorphism group VL and CVL. VL is the automorphism. VL is lattice VOE. G is the automorphism of VL. Is this the module category of CLG? This is pretty equivalent to module category of D alpha G. So if this alpha is pointed, you can this is just inverse problem. You can just this here just said give a holomorphic view. There is a 3 cocycle, but conversely we believe it's true, but we cannot prove it at this point. So there is should be a holomorphic VOE V with the automorphism group G such that the D alpha G module category equivalent to CVG module category. Here just said if alpha is pointed, there is no problem. It's possible. Okay, here I just want to mention one category. Okay, and it's well known the first modern category theory, including future category, module tensor category, and the vertex orbital algebras, both were motivated by trying to understand the 2-dimensional conformal field theory in mathematics. And also this is why we also have a so-called reconstruction program, which says any modular tensor category can be realized as the module category of a rational vertex orbital algebra. So this is called reconstruction program. But this one basically there are not much progress. Okay, but this at least this is the best hope so far. I think here I just review. I think this about this fusion categories and so on. Okay, I just mentioned as and the people here are probably all experts. Okay, a fusion category is overseas the C-linear semi-simple rigid category with found many simple objects, 5-dimensional morphism space. Okay, and also you have unit object, which is simple. You also have this dual, object. Okay, rigid every object has a dual. I use KC for the Grusson-Dicke range of fusion category of C. Okay, and the OC for the set of equivalence class of simple objects. Then, according to Drinfeld-Gelaki-Nikshych-Ostrik, and there is a so-called from B's pair dimension. This means there's unique range homomorphism from KC to R. Okay, the from B's pair dimension of each object is always bigger than or equal to 1. Okay, so this is just from B's pair dimension. And from B's pair dimension, from point of view vertex orbital algebra, this is what we study, literature. We call the quantum dimension. Back then we didn't know much about this category theory. Okay, and so this just in fact is just the we call the quantum dimension in theory of vertex orbital algebra. And also we can define so-called from B's pair dimension of category. This is just a square for being pair dimension, the square sum of from being pair dimension of each simple object. Okay, this is just like I think when we learn so-called semi-simple associative algebra, or when we learn finite group, the order of finite group is equal to the sum of square dimension of irreducible modules. Similarly, for semi-simple associative algebras. Then we they have so-called braided future category. In this case, there is a braiding. You have a future category with a braiding. Okay, and also for each this braiding, there are also a reverse category, and which also braided future category as a future category, and this C bar and the C are the same, but you have with a new braiding. Okay, this is just because CXY is an isomorphism. You can see CYX inverse. This is the new braiding from X tensor Y to Y tensor X. And also, this category is called symmetric if C bar equal to C. Okay, this is just C. We can also, I think we just mentioned this notation already. Two braided future categories are braided equivalent if there's a functor, basically which preserve. I here as very rough, just preserve the braiding. Okay, so here I just called a symmetric fusion category. Okay. Give an example symmetric fusion category. If you have G is a finite group, then you consider the finite dimensional G module. This form a symmetric fusion category. Okay. In this case, from BIMSA pair dimension of this rep G, exactly order of G. Then we have so-called another category called pointed fusion category vector G alpha for any 3 co-cycle. This is just a G-graded vector space with tensor product. It's how we define tensor product. Okay. The associativity of this tensor product is controlled or is determined by the 3 co-cycle. This is how 3 co-cycle occurs here. In this case, because it's a vector space, you consider simple object just in each point G, you have one-dimensional simple object. We call it EG. Okay, just this at the G position is just a C. In other place 0. Okay, in other place 0. Okay. In this case again, this one is pointed because each simple object has one dimension. Okay, so for this pair dimension of this pointed future category and just equal to order of G. So-called pointed just said the from this pair dimension of each simple object is 1. I just mentioned. Pointed means for this pair dimension of simple object is 1. Now I want to mention a result by Delin because this one has something to do with today's talk. Okay, any symmetric future category is braided equivalent to some rep G or rep GZ. GZ as a future category just equal to rep G, but with a new gradient. This new gradient is CUV equal to -1m and V tensor U. Z is a central element of G of order 2. But we know because this because any module comes reducible, Zx is a center element. X on any irreducible G module is a constant by Schur's lemma. So with X on U is just because Z order 2 is just -1 or 1. So this is how we define braiding on this in this rep GZ, just a new braiding. As future category, it's just equal to the rep G. Okay. And it seems rep G corresponds to just view here. Rep GZ corresponding to the Orbifold theory for super vertex operator algebra with G as an automorphism group. Now I just want to mention a Muegge center. Suppose C is a braided future category, G is a subcategory. Muegge center, this is just Muegge center, just talk about the collection of all objects in C, such that when you consider double braiding, this is just equal to identity, okay, for any x in T, for any x in T, okay. This one is a braided future subcategory. And also we use the notation, if D equal to C, and this is called C prime, this one is called the Muegge center of C. And C is non-degenerate if the Muegge center is just trivial, generated by object 1. Okay, generated by object 1. It's of course it's equivalent to the category of finite dimensional vector space. Then of course C is modular I just want to say spherical and non-degenerate. In this case, the modular group SL2Z X on KC. Because in view theory, people often ask why you call the modular tensor category, because modular group X on the Gross-Deacon range. Now I just want to mention this Drinfeld center. Okay, give a category, future category C. Okay, then you can define so-called Drinfeld center. Here, just a standard one. I just recall this object this is called half braided. Then you have this is this one Drinfeld center is a braided future category, and it's from this pair dimension is the from square from this pair dimension of C. Then it's a well-known fact the Drinfeld center of V vector G alpha is a modular tensor category. Okay, and also the center of rep G is also a modular tensor category, which is braided equivalent to Drinfeld center vector G alpha with alpha equal to trivial 3 cocycle. Okay. Now I want to mention another thing called Drinfeld double. Okay, original Drinfeld double is a half algebra tensor is dual. But of course, if G is finite group, I just consider G finite group, then CG is half algebra, it's dual or half algebra. So it's called original twisted double. Then this is Dijkgraaf and Pasquier-Roche in 1990 introduced so-called twisted Drinfeld double, D alpha G. This just as vector space equal CG tensor CG star for alpha is for 3 cocycle alpha. But the product and the co-product are modified by this alpha. Okay, by this alpha. If alpha equal to 1, it's just original Drinfeld double. Okay, this is not half algebra, but this is called quasi-triangular half algebra. Okay, quasi-triangular. But in this case, you have R metric and so on. Meagher, I think in 2003, Meagher pointed out or proved that the module category of twisted Drinfeld double is a module tensor category. The reason for Dijkgraaf-Pasquier and Roche to introduce twisted Drinfeld double is the following conjecture or idea. If V is holomorphic vertex operating algebra, G is a finite automorphism group of V, then there is this alpha such that the VG module category is equivalent to D alpha G module category. But of course, back then, when they introduced this twisted Drinfeld double, there were no concept of module tensor category. This one was only given by 2 years in, I think, 1991. Okay, but the ingredients are given by Dijkgraaf-Pasquier-Roche and later development, just basically indicate this conjecture just in this formula just said, in fact, because this CVG in this case is a module tensor category, DRYG is a module tensor category. These two module tensor categories are braided equivalent. And also I want to mention the module category of DRYG is the twisted Drinfeld double of vector G alpha. These two module tensor categories are also braided equivalent. Now I just use so-called this E just equal to rep G equal to rep G. Okay. Now we can define so-called braided E category. We have this C and I think this called this eta. Okay, you have C is the braided future category, and the eta is embedding. Okay, so E is subcategory. You can consider E is a full subcategory of C. It's a Drinfeld. I'm sorry. It's the Meagher center is just this E. Meagher center is E. So such a category is sort of braided E category. Okay. Then module tensor category M is called a module extension, minimum module extension of C. First, M is a module category with embedding. Okay. Iota M, from C to category M, and also from B pair dimension of M equal to order of G times from B pair dimension of C. If a modular extension of C is called minimal, if the second part you have this relation between these two from B pair dimension M and C. Okay, and also we can talk about the two extension equivalent. Okay. Then I use this MEXTC. This be the set of equivalence class of minimum module extensions of C. You just all minimum module extensions of C. Okay, C is the E category. Okay, up to braided equivalence. Then Meagher has a conjecture in 2002 said this set should be not an empty set. Okay, it's not an empty set. But this one, I think I heard many people talk about this one. Ostrik or other people said, oh, there's some C doesn't have a modular extension. Okay, but it seems this results have never be have never be published. Okay, and this by a theorem of these 4 people, I think I don't know, Brilliant, in Rowell and Wang, they have theorem in 2016 said this set is a finite set. Okay, this is the equivalence class minimum module extensions of C. This one is a finite set. Then I just want to recall so-called regular algebra. Suppose C is braided future category. A regular commutative separable algebra is an object in C with a product. Okay, and also this one is appears in A, just like just occurs once, just one dimensional. And once you have algebra, there's also a solution of this one is I think is introduced by Kirillov and Ostrik. Okay, and you have a solution of E modules, local E modules. Okay, I will not give the definition. Okay, you have E module. I use CE. This is just objects in C. Just this is an E module category in C, and also you have category of E module, local E module. Okay, I use CE0. Okay, CE0 is a subcategory of CE. CE is a fusion category. CE0 is a braided fusion category. If C is a modular tensor category, and then CE0 is also a modular tensor category. Okay. For example, if you consider E, just this rep G, and every regular algebra just have a form, just the CGH star. Okay, this is regular algebra for H here is a subgroup G. And then in this case, EA, because this one is you have algebra, this EA0 just rep H. Okay, this is a result of Kirillov and Ostrik. Okay. Now I just want to so-called relative tensor product. First, you have this Deligne product. You have 2 categories. You have Deligne product, C tensor G. But right now, okay. But we know if you have this so-called canonical regular algebra LC in C tensor C bar. C, do remember we have reverse category. We have C. You have C bar. Okay. This one is regular algebra C tensor C bar. Okay. Right now we just suppose C and D are braided E categories. So in this case, E is subcategory C, E is subcategory D. So C E tensor E bar, because E is a symmetric fusion category. Okay, E bar equal to E. Just E tensor E is a subcategory of CD. Okay, so this one is in CD. Okay, so this one in CD. Okay, so now you can just talk about the okay, here you have the L epsilon. L epsilon is a regular algebra in C tensor D, because you have this L epsilon is an algebra in LE. LE is algebra in E tensor E. Of course, also algebra in C tensor D. Okay, the relative tensor product C and D over E is just you have, because C tensor D you have this regular algebra LE. Then consider corresponding local modules in this category. Okay. So it's called a relative, I think, tensor product. Okay, this because LE is a local is a regular algebra. So here, this theorem, I think, contributed by many people. Okay, they said, okay, the all minimum module extension of E are given equal to the set of all Drinfeld centers based on this pointed future category vector G alpha for all alpha. Okay, and I think this one people know this set are equal. Okay, as I think this is probably known by to Miguel. Many people made a contribution. Kirillov, Drinfeld-Gelaki-Nikshych-Ostrik, but Lan-Kong-Wen in 2017. They find this abstractly is called relative tensor product. They use, of course, as a set, this set of minimum module extension equal to this Drinfeld center. Of course, you can think this one is a group. You have alpha, you have plus beta. Okay, you have alpha plus beta. But this one has a group structure. But use category, they realize this product categorically, this uses relative tensor product. Okay. Another thing is that, okay, if C is a braided diffusion category, okay, and also C contains E, it's Migu-centered G. So in other words, C is a E category. Then you consider all the minimum module extensions of C. Then the minimum module extension of C is tensor for this group, for this minimum extension of E with this action. Action is tensor relative tensor product. So this means the action of this minimum module extension, this group of minimum module extension of E, freely transitively on the minimal module extension of C. This again is the result of Lan-Kong-Wen, okay, in 2017. Now we just okay. Now we just I just come to the vertex orbital algebra part. Here we just suppose V is a vertex orbital algebra. G is a finite automorphism group of V. We assume VG is rational. Okay. And for any, in fact, we use this to teach already. If you use the VOE, I just use CU to denote the V module category. Okay. Here is a theorem in VOE theory. Of course, I didn't mention some other technical assumptions. Okay, but this first resulted by Huang. Okay, which says the module category CU for any rational vertex orbital algebra U is the module tensor category. In this setting, if V is if here our assumption is VG is rational, and there's result by Huang Kirillov Leposky, which says if VG is rational, any extension of VG is rational. Therefore, V is the extension of VG as VOE. VOE extension means VG is a sub VOE of V. Okay, V contains VG, so V is rational. Okay, so V is rational. Now I just introduce about so-called I use irreducible G. This is just irreducible character of G. Okay, for any lambda belong to irreducible G, I use W lambda is a corresponding irreducible G module. Okay. This was a early result joined with Lee and Mason. Then you can have decompose because Gx on V. Then of course V is just you have this direct sum as W V lambda tensor. I'm sorry, W lambda tensor V lambda, because as a module for G is completely reducible, V lambda just a multiplicity of W lambda. Okay. Then then we show each V lambda non-zero and all V lambda and are equivalent to irreducible VG modules. VG module equivalent VG modules. In fact, we prove this for any compact Lie group. If G is compact Lie group, it's okay. The only fact we use in proving the theorem is V is completely reducible G module, or is semi-simple G module. This only fact we use. So therefore, the proof works just for compact Lie groups. So we prove this theorem for compact Lie groups. Of course, any finite group is compact Lie group. Okay, and then we can just use for this one. We can just use epsilon VG be the subcategory, because this each V lambda is a irreducible module for VG. I can consider EVG, which is subcategory CVG. Okay, CVG is a module category of VG. Each V lambda irreducible VG module is subcategory generated by V lambda. Okay, generated by V lambda. Just mean any simple object in this subcategory is isomorphic to V lambda. Then there is a theorem by McRae in 2018, and also by Richard and also I think Ren. Okay, because I think McRae he just basically proved if you have a tensor structure on V on rep G, you can transform this tensor structure or this tensor product structure. This I call the EVG. Okay, EVG. Okay, basically tensor product here. Okay, we just give a functor from the rep gene, okay, to this EV gene. This functor is important, later discussion for the minimum module extension, because when you discuss minimum module extension, we need a pair. We need this embedding. We need this embedding. Okay. So this is just how you give a W. If this W is if a module for gene, you just consider morphism from W prime. W prime is a dual. Okay, we in the serial vertex orbital algebra, we always use prime for the dual, or in the category series, people just use star. Okay, you consider this module this VG module morphism from V prime to V. This is just the this functor. Okay, and then of course we know this CG star is a regular algebra in E. Then this FCG star, this one just as small to VOE. Of course, we know V is a regular commutative algebra in this category in EVG. Okay, so it just maps this canonical canonical regular algebra CG star to this canonical regular algebra CVG star also in EVG in VG. Okay, CVG or EVG. Okay. Yeah, here we just what I mentioned already. This one V is a regular commutative algebra in EVG. EVG subcategory of the CVG. And then of course uses this notation. I use CVGV. This just because with the algebra we use this notation because this one CVG. This is a module tensor category. We use the sub V. This is just V module category in a categorical sense because we have module category. But we also mentioned for VON, there are so-called twisted modules. For any G in G, you have so-called twisted V module category. You have twisted V module category. Then you have, I just consider direct sum of all twisted V module category. Okay, I consider this category. Then, yeah, we prove these two categories. You have two categories. One is from vertex orbital algebras. One is from category. Okay, these two categories are the same. These two categories are the same. In particular, CVG is a fusion category, and the CVG, the local module, and if this one you do remember, we have CE, we have local module in category. Okay, we can consider this local V local module in CVG. This just a V module category. Okay, or you can just see if G equal to 1, just V module category. Here I want to give a remark. Because the module in a category theory, if you have we know this one this is if you have regular algebra, the A module category is a fusion category, so you have tensor product. So from category theory, you have tensor product G twisted module and the H twisted module. This is a GH twisted module. But how to define tiny operators among twisted modules in terms of Jacobi-Lecky identity to give tensor product in a serial vertex orbital algebra is not clear. Okay, of course, if G and H commute, we know how to define, use the so-called Jacobi kind of identity to define the tiny operators and the tensor product. So the advantage to use category theory is we don't know how to define tensor product, use so-called Jacobi-Lecky identity for two twisted modules. Okay, but we know how to do it in category theory. So, but in this we just mentioned these two categories are the same. So we can just use the tensor. But of course, I think Huang defined the tensor product for any twisted modules, but not using so-called correlation functions. Okay, but I just if in terms of Jacobi identity, we don't have tiny operator among twisted modules. Okay. Right now, I just recall this H gene is the holomorphic H is all homomorphic with G action. Okay, here now we just want to mention this CVG. Okay, I think this CVG is the module category of we have this VG category is the minimum module extension of EVG because EVG and E are equivalent. So therefore, CVG is equivalent to the twisted Drinfeld double D alpha G module category for some alpha. Okay, so this basically gave the positive answer to original Dijkgraaf-Pasquier-Roche's, I think, conjecture. Okay. Second one is, of course, then according to our discussion before, is all the CVG, in this case, CVG, in this case, just equivalent to this pointed fusion category, very G alpha, okay? In this CVG, this is just the all the V module category, okay? V module category just the category sense, including module and twisted modules, okay? And in fact, in the V theory, we know for each G with holomorphic, they're unique twisted modules. So this is why, remember, we have EG for this pointed fusion category. In each point, there are only EG one-dimensional module. In V theory, just unique G twisted modules, okay? So it's a pointed fusion category. And also we know for this, if CVG, if CUG, and this one, this is by Lan and Kong and Wen, they have this so-called because minimum module transform group, they have tensor product, epsilon relative tensor product. Then we prove this tensor product in view theory exactly this one is if we use holomorphic with holomorphic, U tensor V against holomorphic. I mentioned GX on U tensor V as diagonal action. So this tensor product exactly given by this one. So we give a better interpretation in terms of VOE tensor product, okay? Relative tensor product, this two module tensor category in terms of tensor product to vertex operator algebras. So just give this interpretation. And again, but in this case, I consider all the minimum module extension of E comes from holomorphic VOEs. So I use the subbing the V extension. Originally, I use M extension. I use V extension. Just come from VOE extension. Come from VOE. This one again is braided up to braided equivalence. As the equivalence class forms finite abelian group. This we cannot prove it's isomorphic to H3. We can only prove it's a subgroup. It's a subgroup. Okay. We can only prove we cannot prove it's full group. Okay. We can only, at this point we can only prove this is a subgroup. Here I want to give a remark, okay, and this is the identity of this group is the CVG with alpha just equal to 1, okay, because we have this alpha, always alpha equal to 1. Then I mentioned this already, okay, and the category series says the minimal module extension of E just the isomorphic to the H3 third cohomology group of G with coefficients in S1. But we also believe and the minimum module extension comes from the holomorphic VOEs also equal to a third cohomology group of G with coefficient in S1. But at this point we cannot prove it, okay? But in order to prove this equal, this just means the following so-called inverse problem of Dijkgraaf-Pasquier-Roche, which says for any finite group G and any alpha, any 3 cocycle, there is a holomorphic VOE in V such that G is the automorphic group V, such that the VG module category is equivalent to twisted Drinfeld double D alpha G module category. So if this is true, then you can prove these two groups are the same. So at this point, we cannot prove this, okay? But if G is a cyclic group or dihedral group of order 2m, m is odd, we prove this are equal. But in general, we don't know how to prove this are equal. We don't know how to prove it's equal. I want to give a second remark, okay? And also, this is for category theory because we know this minimum module extension form a group. So what's the inverse for your element? But each element is a category. The inverse of CVG is just this is called reverse category CVG bar. Okay, so this one is the minimum module extension. But we know because finite group. So because we mentioned the relative tensor product just a tensor product in VU theory. So in this case, suppose the order of CVG this is equal to n. So the reverse module category just equivalent to CV to the n-1g. Okay, because the order of this to n. So in this case, we know how to study this inverse category. Okay, but here for this at this point we want to mention a conjecture which says suppose use any rational vertex operator algebra, we want to find it's a inverse category. Okay, I cannot call reverse. I'm sorry, reverse category. Reverse category. Okay, we want to find it's a bar category. So the conjecture says for any rational vertex orbital algebra, there is another rational vertex orbital algebra W such that the reverse category of CU is just a braided equivalent CW. So in this case, for VG, we know this is true. We just realized this one already. We know this CVG bar is just the another rational VOE. In this case, it's V tensor to n-1. It's still holomorphic. Okay. So in this case, it's just no problem. But I want to just because this one is not known in VOE theory. Okay. We don't know how to find if for holomorphic VOE for rational VOE, CU is a model tensor category. We don't know how to find its reverse category. Okay. Then I say I want to mention a theorem. Okay. Suppose U W are rational vertex orbital algebras, then CU bar is equivalent to CW if and only if there is this holomorphic vertex orbital algebra X such that U tensor W is a conformal subalgebra of X satisfied. So the centralizer of U in X is W. The centralizer of W in X is U. So they are centralizer each other. Okay. Or you can just see this basically is coset theory. Okay. The coset construction, the coset VOE of U is W. Coset VOE of W is U. Just coset. Okay. But here because I didn't give a definition of a coset. Okay. So you can see the holomorphic VOE plays a very important role in this category theory studying. Okay. Now we just come to so-called rational VOEs. Okay, consider all the RGs, all rational VOEs, and the G's automorphism group V. Then we use the FVG because remember we have this so-called VG module category CVG, but every V module restrict to a VG module. So FVG just is a subcategory CVG generated by all VG modules occurs in V modules. Because V is homomorphic, V only has one module. But V is not homomorphic, V maybe has a lot of modules. But in all these modules, you find irreducible VG modules. Because these VG modules generate, this is a subcategory of CVG. I use this one called FVG. Then this theorem says, okay, FVG is a braided future category, and its Milgauss center is exactly the E. So it's FVG is a minimal. Is a braided future category. Its Milgauss center is exactly the E. Second one is CVG is a minimum module extension of FVG. Again, I consider all the module extension, minimum module extension from vertex orbital algebras. Consider all these CWG, okay, up to modular equivalent, up to braided equivalence. This one, again, this one is a finite set, and the group, this one MVEXTC, this X on this set of minimum module extension freely. Again, the action given by this action, the old action was given by Lan-Kong and Wen was the relative tensor product, but here we can realize this relative tensor product in terms of VOE tensor product. U is holomorphic, W is rational, U tensor W is still rational, and still GX U tensor on W. Okay, so it seems the minimum module extension is just a perfect sense for us to study so-called Orbifold theory. Just exactly, it seems just the right thing for studying so-called Orbifold theory. Otherwise, we didn't know what's going on, okay, until we turn our attention to this so-called minimum module extensions. Okay, so at this Milgauss center conjecture, Milgauss conjecture holds for FVG. For this FVG, it always has a minimum module extension. Again, we just expected the module extension of FVG from category theory should equal to the minimum module extension of FVG from a VOE theory. Okay, so this should be the same. Okay. Now, how to see this whole picture? Okay, you can see, and if V is a rational VOE, and you have the subcategory generated by V is the identity in a V module category. The identity, the subcategory generated by identity, this is just the equivalent to the category of finite dimensional vector space. Okay, so this one is embedding to CV. CV embedding to the all this CVG. This CVG is all the V modules, V module plus twisted modules. Okay, this all the include twisted modules. But you just consider the restrictions of each category to VG modules. Okay, if you restrict to V module to VG module, you get a so-called E. This is EVG. You restrict to V modules to the VG modules, you get this FVG. You restrict any VG modules. You restrict all V modules, including twisted modules. You get a so-called VG module category. This is just a collection between the V modules and also VG modules. This is how this minimal extension appears in the picture: E and FVG and CVG. And finally, I want to mention about super orbifold theory and the minimum module extension. And the discussion above also applies to vertical operator super algebra with a finite automorphism group G containing canonical automorphism Z. Because you have super vertex operator algebra, you have even part and other part. So you have canonical central element, which x on even part equal to 1, x on other part equal to -1. This is canonical automorphism. This is automorphism order 2. Then in this case, you can prove this EVG. You have this. You can say the VG module category generated by VG module occurs in V. You have V is the common reducible VG modules. You just consider all the VG modules appearing in V. This generates a subcategory called EVG. In this case, EVG and the rep-GZ are equivalent. So this is what I mentioned. This one is rep-GZ, perfect for the super orbifold theory for super super vertex operator algebras. And McRee also studied this one in 2018. But we studied this one in terms of minimum module extension. Okay. Then of course again, if it's holomorphic, CVG is minimal module extension of rep-GZ. In general, you also have FVG. If V is rational, FVG is a braided rep-GZ category. In other words, this FVG is Milgauss center is just rep-GZ. You also have minimum module extension of FVG. And but more in progress, this means the following. And the minimum module extension of rep-GZ is not known in category theory, even right now today. People in category theory only know few examples how the minimum module extension of rep-GZ is not fully understood. So, but the VOE give you just give you a lot of minimum module extensions. But the first thing we need to classify how to classify the minimum module extensions of rep-GZ. This is just according to the orbifold theory for VOE theory. This is something we need to understand first. Okay, that's all. Thank you.
Thank you, Professor Dong, for the great talk. Let me stop.